Hello, in this video I want to show some extra tools to optimize transition states. Transition states are often not easy to find in any case, so there are many tools that one can employ to get it done. One thing, for example, in the specific case of this SN2 reaction is that one may want to try to twist the geometry a bit more far away from what's some equilibrium structure could be. For example, by enlarging these bond distances. So one can just take bonds, pick these ones and put them, let's say, around 2 angstroms, 1, 2 angstroms, also the other. This could hopefully prompt a better, faster, or more successful location of a transition state. Then, one other thing that one has to always keep in mind is that not all methodologies have built-in analytical Hessian. So, for example, if one does Hartree-Fock but restricted open and has specified calc FC, so to compute force constants before the starting of the geometry, we receive an error because restricted open Hartree-Fock does not have analytical Hessian. How can this then be overcome? One possibility is to first compute, make it just a simple frequency calculation by itself, and in which case the Gaussian will automatically switch to numerical calculation, and then use those force constants by using the appropriate checkpoint file and using read, so read force constant from the checkpoint file. Another possibility is instead to not compute the full Hessian, but to introduce redundant coordinate. So, but before this we can just see all the labels there. There. So we can add redundant coordinates to say specifically to compute numerical Hessian or numeric only for a given set of coordinates. So in this case, since we are approaching with one atom and getting away with the other, the obvious choice for coordinates are the bond 5, 1 and 1, 6. So the carbon chlorine and the carbon fluorine. So what one can do is to add bond, then 5, 1, and then to say that we want to compute the derivative. And then again add bond 1, 6, derivative. So as you see here, now it says that we'll compute numerical Hessian relative only to these bonds. And this will help possibly to create a better transition state. If we can check on the calculation setup, now there is TS and mod redundant, which is the keyword to say that should read this extra input. One more input that can be inserted in opt is to check on the number of eigenvalues that are obtained during the calculation. If one is optimizing a transition state, of course it's looking for a structure with only one negative eigenvalue. But during the optimization, it's possible that can get to a structure where there are no negative eigenvalues, or actually 2 or more negative eigenvalues. And this will prompt the program to stop. but it's possible to prevent this, this behavior by adding one additional keyword here. You can write opt equal no eigentest, and then press update, and then up here comes this the added keyword to opt, and this one can retain it and try to run it. One more thing that one can try is to actually be more forceful in saying that not only these bonds are those that should be computing specifically the Hessian, but it could be actually be those that you say that they are those relative to the negative eigenvalues. To do that, one can again go in redundant coordinates, and instead of saying that for each bond you compute the derivative, you already give a Hessian, so they set the eigenvalue to some number. It's possibly very exaggerate, but why not? You can try to -1. And then here you see that now this is going to be set to -1 in the first step. And of course you can do it also for the other one and just say -1. So in the first step there will be two negative eigenvalues, both of -1 atomic units, relative to these bonds. In practice, this means that we are forcing the optimization to look for transition state along the normal modes relative to these two double bonds. Again, this is quite harsh, but it possibly can get the work done. And with that, good luck with finding your transition state.